Section 6.3 is orthogonal projections. So we're going to extend our notion of the orthogonal projection of a vector onto a line to an orthogonal projection onto a space or onto a subspace. And that's really the whole gist of section 6.3 is to do that. Now, we'll start with an example, and this would be given below, where let the set of vectors S, which is U1 through U4, be an orthogonal basis for R4. And then we let Y be a vector that's this linear combination of U1 through U4. Then we consider the subspace span of U1 and U2, call that W. And we want to write Y as the sum of a vector Z1 and W and a vector Z2 and the orthogonal complement of W. So if you remember the orthogonal complement from section, I believe 6.1, that's the set of all vectors that each vector in the orthogonal complement of W is a vector which is orthogonal to every vector in W. So this is actually a pretty straightforward task, right? We realize that U1 and U2 are the vectors in this subspace W, and we have an orthogonal set here. So each of these vectors is pairwise orthogonal to each other. So we just split up Z1 as being the linear combination of U1 and U2. So that's the component that's in W. And then the complement are these two vectors, because we know that U3 and U4 are perpendicular to vectors, any vector in W, because, well, W is spanned by U1 and U2. So those are our two components, for the component in W being Z1 and the component in W perp being Z2. And we could check orthogonality. Essentially what I just argued here is to take the inner product of Z1 and Z2, and that's this sort of pair of binomials as an inner product. And we just have to distribute all these multiples in the way we'd expect to do so, in the normal way, really. And we see that we have these dot products here, which all of them being vectors which are different from one another, U2 dot with U3, U2 dotted with U4, and so on. Looking over here and all along it, they're all different. So we know that all of these inner products are zero because these vectors are, after all, from an orthogonal set. So this idea of decomposing a vector Y in terms of a portion of it which is perpendicular, or which is in one set, and then as another vector which is composed of vectors perpendicular to that set or in the orthogonal complement of that set, is basically it's the same thing we did before, only now instead of the orthogonal complement, or instead of having a line which was perpendicular to our space or orthogonal to our space, we have a whole space that's orthogonal to that space. So that's really the only thing that's changing here. So the formula should look similar, but slightly generalized. And that's what we see in this case. We have the orthogonal decomposition theorem. So if we have W, a subspace of Rn, then each Y in Rn, so any vector in our vector space Rn, can be written uniquely in the form Y equals Y hat plus Z, whereas before Y hat is in W, or it's parallel to a given vector we're interested in, or it's an element of the space of vectors of the subspace of vectors in W. And Z is perpendicular to that space. So we're generalizing a couple things. It used to be that Y hat was parallel to a given vector. Now it's in a space, subspace. And Z used to be orthogonal to a given vector. Now it's in this orthogonal complement. So it's generalized in two regards, from this being a vector to a space, and from this being a vector to a space as well. But it's not really that much harder to do, maybe a few more calculations, but the formula below, which should look somewhat familiar to us, again, we're seeing this, rational expression of an inner product over an inner product to come up with these coefficients. So this is essentially the same thing we've been doing, but now we're generalizing it to a bigger space. And we're going to check that this is actually the case when we're talking about the space W and W perp in terms of these decompositions. So we have a unique representation in this form. I won't go through the intuition of uniqueness, it follows the standard method of let this be one representation and then let there be another one, y hat plus z1, and then you'll show through, you know, some quick and easy algebraic means that y hat is equal to y hat 1 and z hat is equal, or z is equal to z1, just by writing it down and following what it means for these two things to be the same kind of decomposition. But I will show that this is true. I will show that these are the coefficients of y hat in this decomposition of y. So one of the first things we should note, and then so also just as we did before, we find z by taking the difference of y minus y hat. So we build y hat, the element that's in w first, and then in order to find z, all we have to do is calculate our original given vector of y minus the y hat that we just built, and we'll have our vector z. So let's show that z is actually in w perp, right, or the complement, like orthogonal complement of w. I guess the first thing to note in this is that clearly y hat is an element of the subspace w. Well, why would that be? If we build y hat in this way, we observe that it's a linear combination of the vectors u1 through up. Well, u1 through up is an orthogonal basis. It's a basis of w. So this is a linear combination of vectors in w of the basis vectors of w. So of course y hat is an element of w. So we've got that component, we've got that fact already. So this is guaranteed to be in w, that's fine. Let's show that y minus this vector, in other words, z, is actually in the orthogonal complement. In order to do that, we have to show that for any vector in w, this vector is orthogonal to that given vector. So let's see how we go about doing that. So we'll take, well, here I'm just showing it for any old standard basis vector, uj from this list, u1 through up. Okay, and what we'll see when we do that is that we dot uj and z being given by this expression. And so we write down what that means. So it's uj dotted or inner product with y minus y hat being this vector. It's built by this formula. And we distribute this, or we write down first what y hat is. Again, that's this larger expression here. And that's written into here. Now, uj dotted with y leaves us with this term. And then uj is dotted with each of these terms along u1 through up. Well, let's remember u1 through up is an orthogonal basis. So uj is orthogonal to ui, every one of these u1s through ups except for uj, except for itself, right? So we know that that's the only one that's non-zero. The rest of those inner products are zero. So most of those terms fall out, and all we're left with is this first multiple and then minus the term that matches uj. So this, and so overall our uj dot z is equal to this highlighted expression at this point. When we look closer at the larger expression in this right hand side, and we see that, well, we have a uj inner product with uj in the denominator and in the numerator here. So these two actually cancel, two highlighted terms cancel, and we're left with uj dot y minus y dot uj. And thanks to the fact that inner products are commutative, these two elements are the same. So we're subtracting something from itself and we get 0. So now I've only shown this for one, a basis vector in W, but notice this, uj is any one of the basis vectors in W. It's u1 through up, it's any one of them. So the next thing we could do is I didn't take it to this generality, but we need to show that it's perpendicular to every vector in W, right? So what you would need to do really is to write a vector v that's equal to a linear combination of all of these u1s through this u1 through up, and then we run it through a similar process. But what we'd realize is that since any time we dot one of our basis vectors with this vector z, we're going to get 0. It's just going to fall out. The details are just going to be large. We're going to have p of these expressions show up when we write a vector v and z that's dotted with or v and w that's dotted with z, this vector z, and what we'll find is that p of these expressions just sum to 0 as we see here. So it's not entirely necessary to carry that out. So what we see is that z is perpendicular to or orthogonal to every basis vector uj and w. And since that's the case, we can extend that to any linear combination of vectors in w being perpendicular to z as well. So now we see that this vector z that we can construct is clearly in the orthogonal complement of w. So again, this is just a generalization of what we did when w was vector u. Now we're talking about w as a space. So we can decompose any given vector with a component in a space and then plus a component of it that is orthogonal to that space. So in practice, we'll look at this example here. We've got two vectors u1 and u2, and we're given a vector y to go along with that. They're all in R3. We want to show that u1, u2 is a basis for w being the span of u1 and u2. So there's a couple of ways we could do this. We just need to show that they're linearly independent. So you could check that whether or not they're scalar multiples of each other. We also know that orthogonal vectors are linearly independent. So if their inner product, u1 and u2's inner product is 0, well, then we know that they're linearly independent. And I think if you check that, you realize that it is 0 and it is linearly independent. However, I did argue down here the old way of saying that, well, if u1 is equal to some scalar k times u2, well, this is true if and only if, when we write the details in, this is negative 240 for u1 is equal to 2 times k plus 1, or 2 times k and 1 times k and 1 times k down this vector's entries. And if we look at least the last two lines here, we see a contradiction. 4 is equal to k and 0 is equal to k. Well, k can't be both 4 and 0, so there's no such k which this is true. So I used an elaborate, probably overwrought proof by contradiction to show that there is not a scalar k such that u1 is equal to k u2. So these two vectors are not linearly dependent. It's usually easy to spot check and just look at them and see they're not multiples of each other. So they're not linearly independent. This is when we're given two vectors in a set. So that's one way to do it. Again, there's a comment down here, u1 dotted with u2 is 0. So we know that the two vectors are in fact orthogonal, which means they are additionally linearly independent. That was a result back in section 6.2. So now we need to decompose y in the fashion that this formula tells us, right? So we only have two vectors, u1 and u2. So we're only going to have two terms that look like this. So we'll stop at u2. And when we write that formula here, this is what it is in this case for our two different vectors, u1 and u2. And we have y dotted with u1 here over u1 dotted with u1 times u1, the vector. And we do that same thing with y and u2, y dotted with u2. We should see that this is part of that step. And then u2 dotted with u2 and then times the vector u2. And when we put all of this together, we end up with this vector here. So this is our y hat vector. This is the vector that's in the subspace w, right? It's in the span of u1 and u2. Of course it is, because it's a linear combination of u1 and u2. And then to find z, we just write z down as the difference of y and y hat. We just subtract out the component of y that's in the subspace w in order to get the component of y that's in the orthogonal complement w perp. And that looks like this. Here's y minus our vector y hat here with some simplifications. And then we end up with this as our z vector after we simplify the arithmetic. And then our decomposition of y is our vector y hat, again with some simplifications of those fractions, plus this vector z. And what we can check is that this vector here is linearly dependent to our vectors u1 and u2. If we really wanted to put that in a matrix and see that we get a dependence out of it. And then we could also check that the dot product of this vector with either u1 or u2, or actually both, is 0. So the inner product of this with the vectors u1 and u2 is 0. But we don't have to, because we know that, and that's just the method of checking this. But we know that we've used a formula or theorem that tells us that this is how to do it, and that's correct. And we've seen roughly the proof of that. So we accept that as long as we've done our work correctly, we've got the correct answer here. So yeah, to check it, this should be linearly dependent on u1 and u2, or the vectors of our basis, and this one should be orthogonal to the vectors of our basis. Now, the best approximation theorem. So this is not the best approximation theorem. It's the closest point approximation theorem is the way to think about it. So here's a sketch to help us kind of get an idea of this. If we're talking about a space W, and then we have some vector y, right? So all of my vectors in this drawing, by the way, this figure, are represented by their terminal points, right? I just drew a point at the terminal end of the vector, and that's what we're talking about. Essentially, a point in space is the way to think about it. If we're talking about y and its closest point to this, its closest distance to the space W, it's going to be an orthogonal line to W, right? We're going to draw a line that goes straight to W, right? Anything else is going to result in a longer distance from y to the space W. We see that from y to y hat and from y to v. It's longer to go to v than it is to go to y hat from our vector y. So our closest point is really in an orthogonal point. So the best approximation to y, if we're in the space W, is y hat. So that's what this theorem is telling us. And they give us it even further. They say that this is the best approximation in the sense that the distance from y to y hat, here to here, this distance right here, is less than the distance from y to v for any other v that we could find in W. The other dots might represent v's and w's that I've highlighted there, v's in the space W. And those are all further from y hat, or further from y than y hat is, right? The orthogonal projection is the closest point in W to y. So that's what this is telling us. For any other v, its distance is going to be greater than y minus y hat. So we just need to prove that this is true. I think geometrically, we absolutely accept it. It meets intuition. The closest point from a point to a plane, or we draw W as a plane because it's harder to draw render a three-dimensional subspace on a page, right? It's a little bit easier to show that this is, this is a three-dimensional setting. This point here is off of this two-dimensional space. But we just write W generally as some subspace. It could be of any dimension, and this really works for any dimension subspace. So in order to do this, we need to write this down. Y minus v, we can subtract and add y hat to this difference. And then we can regroup the terms. Notice that if we simplify the right-hand side, we'll get the left-hand side, y minus v. But with this in place, and then knowing that y hat is the orthogonal projection of y onto W, we realize that this forms a right triangle. So the length between y and v squared, so that's this part in the formula here, y minus v, its length squared is the hypotenuse of a triangle whose other lengths are y minus y hat and y hat minus v. So there's those other parts. Y minus y hat and y hat minus v. Right? So through the Pythagorean theorem, we know that the hypotenuse squared, so the length of this, which is y minus v, magnitude, right, norm, square that, is equal to y minus y hat length squared, and then y minus v, or y hat minus v length squared. And now we know that, well, the smallest that y minus v is ever going to be is 0, and that's only if v is actually, yeah, this is fine. That's only if v is not y hat, and we've already said up here in the theorem that for all v and w distinct from y hat, so for all v that are not the vector y hat, we have that this is the case. Well, if v is not y hat, then this length is non-zero no matter what. So what we see is that if we add this non-zero amount to this length, whatever it is, this quantity squared, well, we know we're going to get something that's greater than this quantity, which is just this part. Right? So in other words, what I'm saying is that this is something that's greater than zero, and it makes whatever this overall value is greater than just this value by itself. So what we have in the end is that this difference, or this length squared, is less than this length squared. We take the square root of both sides, well, then we have exactly what we have above. And we'll take just the positive square root, and that'll work out exactly as we'd hoped for. So that's our geometric argument that, or sorry, our geometric intuition, and then our analytic argument to show that this is actually the case. Our closest point from Y to any subspace W is the point that's is the orthogonal projection of Y onto W. So let's implement this in a problem. The distance from a point Y and Rn to a subspace W is defined as the distance from Y to the nearest point in W. So in other words, from Y to its orthogonal projection. So there's a lot under the surface here, right? This is really fundamental to optimization problems, and that's what we'll see by the time we're done with chapter 6. To find the distance between a point and a subspace that we're interested in, this subspace, if you think about it in terms of old calculus problems, this is our constraint set, and we're trying to find a Y value that's a point in our constraint set that's as close to this point Y as possible, potentially, and that's to minimize or maximize cost or something. So in the background of all of this is that really nice application that we'll get to see a little bit of by the time we're done with this chapter. So anyway, let's just do this mechanical practice though, right? We're just asked to find the distance from Y to W. And again, we've been told that that's Y to its nearest point in W, which is its orthogonal projection onto W. So the distance from Y to W, well, and W is the span, sorry. So now we're given that W is the span of these two vectors, U1 and U2. And we're asked to find the distance between this vector Y and this subspace W. So what we need first is the orthogonal projection of Y onto W. Well, we should check that we have whether or not we have an orthogonal basis for W, right? And the way to do that is to note that their inner product is 0, or to check that that's the case. And if we carry this out, we'll see that that's in fact true. The inner product of these two vectors is 0. So we know that we have orthogonal basis vectors. Now we can determine the orthogonal projection of Y onto W, which is given by Y hat, through our formula from the previous problem, right? Or theorem and problem, actually. So back here, we'll just run this formula once again for two vectors. So this is a Y1 dotted, or Y dotted with U1 over U1 dotted with U1 times U1. Same thing for the vector U2. Y inner product U2 over U2 inner product with itself times U2. And when we simplify this, we have some of these two vectors, and writing Y hat as one single vector, we get -1, -8, 4. So that is the projection of Y onto W. So Y hat, that's the vector that's in W that is closest to Y. It's exactly as this drawing right here is indicating, right? Y hat is the closest thing in W to the point Y floating out there in space, or in space that's not W. So the problem is actually asking for the distance from Y to the set. So all we need to do now is calculate the distance from Y to Y hat. We know that Y hat is the closest vector in W to Y. We just find its distance to Y, and we'll have it. And this is just a simple matter of carrying out the distance formula applied to Y and Y hat, which is really just the norm of their difference. And that comes out to root 45, which when we take a perfect square of 9 out, we have 3 root 5. And that's our distance from Y to this subspace W. Now, some more tools for this. remember we talked about an orthonormal basis in the previous section. So if we have an orthonormal basis, our formula from providing the projection of y onto w actually simplifies by a little bit. And this is a pretty easy thing to see. So I'll walk through an intuition for the proof down below. But remember that generally the formula is y dot u1 over u1 dot u1, but we're missing that denominator now in this situation, and that's thanks to the fact that this is an orthonormal basis. There's another way to write this in terms of a matrix with orthonormal columns, or if U is the matrix formed by putting these vectors U1 through UP as the columns of a matrix, then we've got this other formula, and I'll walk through a sketch of each of these things proofs. But remember that generally this a term of this form fits in for each of these coefficients, right? U1 dot U1 in the case of the first element. Well, one thing we should remember now, since we have an orthonormal basis, is that U1 dot U1 is equal to 1, or UI dot UI is equal to 1 for every one of these P orthonormal basis vectors. Since it's an orthonormal basis, all the vectors have length 1. So their inner products with themselves is 1. So now anything that would have been a denominator, U1 dotted with U1, well, that denominator is just equal to 1. So we can just drop that term. So that makes finding a projection all the better. If we have an orthonormal basis, well then projection of y onto that set is just this simple formula. So that much easier to carry out the calculations of. So right, U1, UI dotted with UI is just 1, and that leaves us with these terms that fill in all of our 1 through P spaces there. So that one was easy to see. The next one's just a matter of notation, right? So U transpose times Y. Remember, U transpose is the matrix U in which the columns have been switched to rows. Well, if I write U transpose Y down first, so first this matrix product, and then I'll multiply what the result of this by U in order to get the full matrix product. But U transpose Y is equal to, so I write down my column vectors, but they're now rows. U1 transpose as a row through UP transpose as a row. And I know that when I multiply this row times this vector, I have, it's essentially the inner product of U1 and Y, right? This is a row vector times this column Y. So I get for each of my P entries here, U1 dotted with P down to, or U1 dotted with Y down to UP dotted with Y. It's just a matter of notation for the matrix, right? And then I multiply this result by U, and I know that, well, U times this vector, remember this is a vector here, comes out to, well, it's the linear combination of the columns of U using the weights, the columns of U using the weights of this vector. So it's the column U1 with weight U1 dot Y, right? It's the column UP with weight UP dot Y. And when I look at what this formula is, I realize, well, that's exactly what my projection formula above is. So yet another way to calculate the projection of Y onto W, or at least another way to write it, is to write it as U times U transpose times Y, where U is the matrix whose columns are our orthonormal basis vectors. So just more tools for writing these projections or calculating them. And that really is it. There's most examples are similar to what we've done. You're just going to use these formulas to find projections of vectors onto subspaces and maybe answer a couple questions related to those types of projections. In section 6.4, we're going to find a way to actually build an orthonormal or orthogonal basis through the Gram-Schmidt process, which is sort of our ultimate tool here, because now we see the utility of these bases, these orthogonal sets of vectors. We'd like to be able to come up with them if we so desire one. In section 6.5, we'll see the application of these things, where we'll talk about least squares problems. And that'll finish our course up once we get done with both of those two videos.